Here is the combined summary. The authors propose utilizing Transmon Qubits as a novel detection mechanism for dark matter with low energy deposition, calculating dark matter-induced quasiparticle densities in Transmon Qubits and providing one of the strongest existing lab-based bounds on dark matter-nucleon scattering below about 100 MeV. They strongly constrain subcomponent dark matter, considering both a dark matter population thermalized in the Earth and the dark matter wind from the galactic halo. Transmon Qubits can detect dark matter with low energy deposition, including both light dark matter and heavier dark matter that has become bound to the Earth, by measuring power fluctuations in single quasiparticle devices. The authors consider two potential dark matter components: the dark matter wind from the galactic halo and a thermalized dark matter population bound to the Earth, detailing the dark matter density and velocity inputs for these components. The calculation of scattering rates and energy deposition is detailed, focusing on very low energy depositions appropriate for light dark matter or low velocity dark matter. Interatomic forces are important in this regime, with lattice vibrations or phonon excitations providing the dark matter scattering rate. The total scattering rate per unit target mass is calculated, taking into account the dark matter velocity distribution, target density, dark matter nucleon scattering cross-section, reduced mass of the dark matter nucleon system, and the dynamic structure factor. The phonon density of state for the target material, aluminum, is provided, showing the resonant energy transfer that can occur between dark matter and the detector. The study maps out future sensitivities for dark matter nucleon scattering, including subcomponent dark matter candidates, and demonstrates the potential of Transmon Qubits as a novel detection mechanism for dark matter with low energy deposition. Here is a combined summary of pages 58 of the research paper. The authors investigate the possibility of using superconducting materials, specifically aluminum, to detect dark matter. They employ the dark ELF code, modified for a single atom in the primitive cell, to calculate the dark matter-induced quasiparticle density in aluminum. The authors assume a quasiparticle generation efficiency of 60% and an energy gap of approximately 340 micro-eV for aluminum. They find that the quasiparticle density is related to the dark matter power injection and plot the dark matter-induced quasiparticle density in aluminum for 3 benchmark temperatures. The authors also consider other single quasiparticle devices, including a low-noise bolometer and super CDMS-CPD, which can produce weaker but supporting bounds. They derive new bounds and sensitivities for spin-independent scattering using a Transmon Qubit, assuming the incoming galactic dark matter makes up the full relic abundance. The bounds on halo dark matter are stronger than lab-based experiments below about 100 MeV. The authors present new limits on the dark matter-nucleon spin-independent scattering cross-section using Transmon Qubit measurements for the Earth-bound dark matter population. They compare their results with existing limits from astrophysical systems and lab experiments, demonstrating the strong constraining power of Transmon Qubits. They assume a recombination limited quasiparticle density modeling and consider various fractions of the dark matter density, labeled as Fchi. The authors show that their bounds are not largely changed even when the dark matter density is decreased, while other experiments weaken or disappear. They highlight that their bounds are largely evaporation limited, not detector sensitivity limited, and discuss the importance of considering evaporation. The figures display the new constraints on the dark matter-nucleon spin-independent scattering cross-section as a function of dark matter mass, for varying fractions of the dark matter density, demonstrating the strong constraining power of Transmon Qubits even for subfractions as small as 10^12. This research paper explores the potential of Transmon Qubits in detecting low-energy dark matter interactions, leveraging their low quasiparticle density to enhance sensitivity. The authors discuss 2 dark matter components: light dark matter from the galactic halo and thermalized dark matter bound to the Earth. Transmon Qubits offer an energy deposition detection threshold as low as approximately 1 MeV, 6 orders of magnitude lower than standard direct detection setups, achieved through Cooper pair breaking and quasiparticle release. The paper presents new constraints and future sensitivities for both dark matter components, focusing on the thermalized population. Recent proposals suggest this population could be detected, especially if dark matter scattering with the detector makes up some subcomponent of the full dark matter relic density. The study also discusses the sensitivity of Transmon qubits to particle dark matter models that do not evaporate at very light dark matter masses. The authors conclude by emphasizing the potential for new low quasi-particle density devices to probe dark matter with low energy deposition, as they are actively created for applications such as quantum computing, infrared telescopes, or radiation detectors. The paper identifies limitations, assumptions, and future work discussed, using precise language and domain-specific terminology. The authors provide an extensive list of references, citing various studies and research papers in high-energy physics, cosmology, and astrophysics. These references span topics including dark matter searches, particle physics, and cosmological observations, demonstrating the ongoing efforts to detect and understand dark matter. The cited works highlight the importance of understanding the interplay between dark matter and dark energy in shaping the evolution of the universe, as well as the challenges and opportunities facing researchers in these fields.